Welcome to the lesson on working principles and components of electric motors. By the end of this lesson, you will be able to explain the basic operating principle of electric motors and understand how they convert electrical energy into mechanical energy. You'll gain insight into the concept of regenerative braking, a key feature in many electric vehicles. You will also be able to identify and describe the main components of electric motors, including stators, rotors, windings, and bearings. Let us start with the fundamentals of magnetism. Magnetism is a form of energy that is caused by the motion of electrons in certain materials. Although invisible to the human eye, just like electricity, magnetism is a powerful force. Magnetite is the most common naturally occurring magnet, but many other materials can be artificially magnetized to some degree. The north pole of a magnet is the end that, when freely suspended, points towards the Earth's geographic north pole. The south pole of a magnet is the end that points towards the Earth's geographic south pole. The poles of a magnet are inseparable, meaning that if you break a magnet in half, you will not get a separate north pole and south pole. Instead, each piece will become a new magnet with its own north and south poles. When two magnets are placed close together, their interaction depends on the orientation of their poles. If unlike poles, that is north and south, are brought close to each other, the magnetic lines of force exit from the north pole of one magnet and enter the south pole of the other, resulting in an attractive force between the magnets as seen in Figure A. On the other hand, if like poles, that is north and north or south and south, are placed close together, the curving flux lines of the magnetic fields meet head-on, causing a repulsive force that pushes the magnets apart as shown in Figure B. This attraction and repulsion between magnets is a fundamental property of magnetism and is determined by the direction and orientation of the magnetic lines of force. Magnetic lines of force create a field of force around a magnet, which is caused by the alignment of groups of atoms in the magnetic material. These lines of force leave the north pole and return to the south pole of a bar magnet. Magnetic induction is a phenomenon where a non-magnetic material, such as iron or steel, becomes magnetized when placed in an external magnetic field. This occurs because the external magnetic field aligns the magnetic domains within the material, causing it to acquire magnetic properties. In other words, when a piece of iron or steel is brought close to a magnet, the magnetic field of the magnet induces a magnetic field in the iron or steel, effectively turning it into a temporary magnet. The induced magnetic field in the material will have its poles aligned with the external magnetic field. Let us look at the concept of electromagnetism. Electromagnetism is a phenomenon where a magnetic field is generated around a current-carrying conductor. Electromagnets, which are based on this principle, can be many times stronger than conventional permanent magnets. To create a simple electromagnet, you can take a nail and wrap it with about 20 turns of insulated wire. Connect the ends of the wire to the terminals of a battery, and the current flowing through the wire will create a magnetic field around the nail, turning it into an electromagnet. When an electric current flows through a wire, it generates a magnetic field around the wire. The shape of this magnetic field depends on the shape of the wire. If the wire is straight, the magnetic field forms concentric circles around the wire as seen in the Figure A. However, if the wire is looped into a coil as in Figure B, the magnetic field resembles that of a bar magnet, with field lines flowing from one end of the coil to the other as seen in Figure C. The magnetic field generated by the current persists only as long as the current continues to flow. If the current stops, the magnetic field collapses. This relationship between electric current and magnetic fields forms the basis of electromagnetism and is essential for understanding the operation of various electrical devices, including electromagnets, transformers, and motors. Electromagnetic induction is a phenomenon where a changing magnetic field induces an electric current in a conductor, or conversely, a changing electric current in a conductor creates a magnetic field. This principle is the foundation for the operation of electric motors. In an electric motor, electromagnetic induction is used to convert electrical energy into mechanical energy. Now let us talk about the working principle of electric motors. The working relies on the motor effect, which occurs when a current-carrying wire in the shape of a rectangle is placed in a magnetic field. The wire experiences a force, and the direction of this force depends on the direction of the magnetic field and the current flow. Fleming's left-hand rule can be used to identify the direction of force. In the configuration shown in the image, the left side of the wire experiences an upward force, while the right side of the wire experiences a downward force. As a result, the wire starts to spin clockwise. This motor effect is the foundation for the operation of electric motors, where the interaction between the magnetic fields of the stator and the rotor, along with the current flowing through the rotor windings, creates a torque that causes the rotor to rotate. As soon as the wire finishes a half turn, the force on the left side acts towards the bottom and the force on the right side acts towards the top, which makes the wire spin back to its original position. This makes the wire unable to complete one full turn. To ensure the continuous spinning of the wire in an electric motor, the direction of the current needs to be changed every half turn. This is achieved using a split ring commutator, which swaps the positive and negative connections every half turn. Brushes maintain contact with the commutator, ensuring a continuous flow of current to the wire. As a result, the direction of the current in the wire swaps every half turn. This configuration ensures that the forces acting on the wire will always be acting in the same direction, allowing for the continuous rotation of the wire. It is important to note that this mechanism, utilizing the split ring commutator and brushes for enabling uninterrupted operation, is characteristic of a specific type of electric motor known as a brushed motor. In brushless motors, the motor effect is achieved through electronic commutation rather than using brushes and commutators. An electronic controller in this system ensures that the magnetic fields are consistently oriented to produce continuous rotation. The physical structure of a brushless motor differs from its brushed counterpart, with the stator containing the windings or electromagnets and the rotor consisting of permanent magnets. To increase the speed of rotation in an electric motor, several approaches can be taken. One method is to increase the current flowing through the wire, as a higher current will result in stronger magnetic fields and, consequently, greater forces acting on the wire. Another approach is to add more turns to the coil or wire, which will enhance the magnetic field strength and increase the torque experienced by the rotor. Increasing the magnetic flux intensity by using stronger magnets in the stator will also contribute to faster rotation speeds. Let us now shift focus to the concept of regenerative braking. Regenerative braking is a remarkable feature of electric vehicles that improves energy efficiency. During braking or deceleration, the electric motor takes on the role of a generator. As the driver applies the brakes, the wheels continue to turn the drive shaft, which in turn rotates the conductor inside the motor. The rotating conductor cuts through the magnetic lines of force created by the stator, inducing a voltage and current in the windings, as discussed in the electromagnetic induction topic. This process effectively converts the vehicle's kinetic energy, which would otherwise be lost as heat during braking, into electrical energy. The inverter then comes into play, converting the generated alternating current into direct current that can be fed back into the battery pack. This illustration aims to demonstrate the opposite processes of energy flow and the role of the electric motor in normal motor mode and braking generator mode. During normal driving, the energy flow starts from the battery, which stores electrical energy. The inverter then converts the DC power from the battery into AC power, which is fed to the electric motor. The motor, in turn, converts the electrical energy into mechanical energy, which is used to propel the wheels and drive the vehicle forward. On the other hand, during braking or regenerative mode, the energy flow is reversed. The kinetic energy from the wheels is transferred back to the motor, causing it to act as a generator. The motor converts the mechanical energy into electrical energy, which is then processed by the inverter, converting AC back into DC. Finally, this electrical energy is stored in the battery for future use. This illustration highlights the versatility of the electric motor and the efficiency of regenerative braking in electric vehicles. There are several key benefits to regenerative braking in electric vehicles. Firstly, it recaptures kinetic energy that would otherwise be lost as heat during braking or deceleration, improving the overall energy efficiency of electric vehicles. By recovering and storing energy during braking, regenerative braking helps to extend the range of electric vehicles, allowing them to travel further on a single charge. Additionally, regenerative braking minimizes the use of conventional friction brakes, reducing wear and extending their lifespan, which leads to lower maintenance costs. Finally, the recovered energy is stored in the battery, reducing the depth of discharge and helping to maintain the battery's health and long life. Let us now move on to introduce the main components of a generic electric motor. As illustrated in the image, some of the main components that make up an electric motor are the stator, stator winding, rotor, bearings, shaft, housing, terminal box, cooling fan, and end bells. It is important to note that not all electric motors will necessarily have all of these parts, as designs can vary depending on the motor's specific purpose and application. The stator is the stationary part of the motor that contains the stator windings, which are coils of insulated wire wound in the stator slots. When energized, these windings generate a magnetic field. The rotor, on the other hand, is the rotating part that contains either rotor windings or permanent magnets. It interacts with the stator's magnetic field to produce torque, which causes the rotor to rotate. Bearings are mechanical components that support and guide the motion of rotating parts, such as the rotor. They are designed to reduce friction and wear by allowing the rotor to spin smoothly and efficiently within the motor housing. The shaft connects the rotor to the load, transmitting the mechanical power generated by the motor to the desired application. The electric motor consists of several additional components that are essential for its proper functioning. The frame or housing is the outer structure that provides mechanical support, protection, and mounting points for the other components. Attached to the frame is the terminal box, an enclosure that houses the electrical connections between the motor windings and the power supply, ensuring a secure and reliable connection. To dissipate the heat generated by the motor during operation, a cooling fan with a protective cover is often incorporated into the design. However, it is worth noting that motors in battery electric vehicles are generally cooled by liquid cooling systems, which are more efficient for handling the high heat loads in EV applications. Finally, the end bells are removable covers located at each end of the motor frame. They serve to support the bearings and provide access for maintenance and repair, allowing for easy servicing of the motor when necessary. Let us now summarize what we have learned in this lesson. Electric motors convert electrical energy into mechanical energy using the principles of magnetism and electromagnetic induction. The interaction between the magnetic fields of the stator and rotor, along with the current in the rotor windings, creates a torque that causes the rotor to rotate. Electromagnetic induction is the foundation for the operation of electric motors, where a changing magnetic field induces an electric current in a conductor, or a changing electric current creates a magnetic field. Regenerative braking improves energy efficiency by converting the vehicle's kinetic energy back into electrical energy during braking or deceleration, which is then stored in the battery. The main components of a generic electric motor include the stator, stator windings, rotor, resolver, bearings, shaft, housing, terminal box, cooling fan, and end bells, each serving a specific function in the motor's operation. Thank you.